Hello.
Good evening, sir.
Good evening. Why no one has joined? You received the mail, right? Regarding the
Yes,
class?
yes, sir.
Okay. So you wait for 2 more minutes, then we'll start the class.
Okay.
Hi, very good evening to you all. So let us start today's class. Okay. So till last class, we were seeing about data structures. Okay. So now, like today, we're going to start with the algorithms. Okay. So what exactly is an algorithm? So you have studied in your college or in your schools and all you studied. So what is the definition for an algorithm? So that's the famous definition, right? A step-by-step procedure to solve a problem is called an algorithm.
Yes.
Okay. So the same thing holds. So algorithm is nothing but it is a step-by-step procedure to solve a particular problem. Okay. So now, um, so if you take any problem, so first what happens is you will be writing an algorithm. So why do we need for an algorithm is that it is universal. Okay. So if you write it as a program, what happens is someone would be able to understand. Okay, if they know the language. Like for example, you are writing a program in Python. Okay, the person who knows only Java doesn't know Python, then he will not be able to understand what have you tried to done, right? So whereas if you give an algorithm, so you'll be able to convert it to a Java code. So that is the first basic use of an algorithm. Okay, and one more thing is so in the first 2 3 classes itself, I told you that there is a 80-20 rule, right? Okay, so 80% of your time you should spend in your paper, so working out the logic, right? So like if you write an algorithm, you will understand what is the flow of the program, whether you will be able to logically implement a particular program or not.
So working
Okay.
out the logic.
Yes. Okay. Okay, and so what is the feasibility of the program? Feasibility in the sense whether it is implementable or not. Like, okay, so how much memory it takes and how much time it takes to perform a particular logic. Okay, so all those things can be done using an algorithm. Okay, fine. So the first thing is we're going to analyze an algorithm. So actually, algorithm is a step-by-step procedure. Solve a problem. So the second thing is we need to analyze an algorithm. So only if you analyze an algorithm, we'll come to know how much memory would be needed to execute a particular program or how much time it needs, okay, to execute a program. Okay. So basically we're going to analyze using space, which is also memory, and time. Okay. So now let us focus more on time. Okay, because space is enormous, right? So, but still, I don't tell that you can take any amount of space. Okay, but still we have enough amount of space. Only thing here is the time should be like uh, like optimized. Why in the sense? Okay, again, I will come to the same example which I told you while starting of data structures. So there will be millions of users using a particular website, right? So even if there is a microsecond delay, it will get multiplied by millions. Okay. So that is why we should focus more on time. Okay. Complexity of algorithm. Are we going to discuss it? Yeah, yeah. We're going to discuss on complexity of algorithm. Yeah. So now, um, so we should understand what are the different complexities available. Okay. The first, so we'll write it in increasing order, ascending order. The first one is the constant complexity. And before that, denotion of the complexity. So there are three different cases. One is the best case, average case, and then worst case. So you should know what is this best case and what is the average case and what is this worst case. Let us take a simple example. Let us say you have a list of elements, okay, in a shuffled order, and you're going to search for a particular element. Okay, so sometimes there's a possibility that your search element is at the first location itself. Okay, then there is no need for searching the entire list, right? Okay, at the first search itself, you will get the output. Okay, that is called your best case. Okay, and then the worst case is that, okay, that element which you are searching does not exist in the list at all. Okay, that is your worst case. You have to search for the entire list to come to know that the element is not present. So that is your worst case. And another worst case may be if the element is present at the last location. Okay, even in that case, you have to search the entire list. An average case is if the element you're searching is present in the middle. Okay, anywhere between the first and the last is called the average case. Okay, so best case is denoted by small o. Okay, the small o. Average case is denoted by theta. So you know the theta symbol, right? Okay, theta. And then the worst case is denoted by capital O. That is big O. So small o and then big O. Okay. Are we allowed to ask questions during the lecture? Yes, of course, you can ask questions. You can like switch on the mic, turn on the mic, and then you can ask the question. You can unmute and then ask the question if you want. Okay. Yeah. So worst case is denoted by big O. Yeah. So, always what you have to do is you're going to analyze a particular algorithm using its worst case only. Okay, why worst cases? Okay, so only then you can like understand what is the maximum time that will be required to solve that problem, right? Okay, so sometimes the best case may be the first one, but if there are 1 lakh elements, so you cannot waste
You
1
can
lakh
ask
time.
questions.
Okay, we cannot waste 1 lakh amount of time, right? Understood? Okay. So instead of having the worst case 1 lakh, if it is possible to reduce the complexity, okay, then we have to go for that. If there is a reduced algorithm, okay, you're able to understand. So always you have to analyze an algorithm based on its worst case. Okay. Yeah. So constant complexity. So it is denoted by order of constant big O of either 1 or C. Okay, some constant value, order of 1. Okay, so can you tell any example? Somebody knows, you can tell me for constant complexity, whatever might be the value of n. Any example for a constant complexity algorithm?
Linear search. No,
Hmm?
no, no, no.
Okay, so you know the sum of n natural numbers formula, right? So what is the formula for sum of n natural numbers?
N into n plus 1 by 2.
Yeah, so it is nothing but n into n plus 1 divided by 2. Okay, so there is other way of calculating sum of n natural numbers also. Okay, so how you will do is you will just put a for loop, start the loop from 1, and then iterate the loop till it reaches n, and then keep on adding the values one by one to a sum variable. Okay, that is the other solution. Okay, so whereas that solution will run or will take a loop that will run for n times, right? N natural numbers, so a loop will run for n times. So the complexity is order of n. Okay, if there are n calculations, then the complexity is order of n. So whereas here, whatever might be the value of n, it is going to do one multiplication, one addition, and one division. That's it. Only 3 operations. Whatever might be the value of n. Even the n value is 1 lakh also, there are only 3 operations. 2 lakh also 3 operations. 5 also only 3 operations. Got it? Okay. So that is called constant complexity. So it doesn't depend on the variable at all. Okay. And all the mathematical formulation type of problems will take a constant complexity. So that is why while solving a problem, you should check whether that particular problem can be solved using any mathematical formula or not. Only if it is not possible, you should go for different strategies. Okay, so we'll discuss on that later. So order of 1. The second um, complexity which comes in order is, any guess or anyone wants to answer?
Okay.
Yeah, log of n. Okay, so any example for log n complexity? Log n complexity, any example? Binary search. Some of you would have heard about it. Yes, if you don't know, not a problem. We'll discuss this problem step by step. Okay, in the next class. Okay, binary search. So this takes order of n. Okay, and I will discuss, just if you don't know anything about binary search, not at all a problem. We'll be discussing the entire concept in the next class. Okay, and the next thing is order of, yes. Yes, what is the next higher complexity? It is order of n. Okay, so any example for order of n algorithm?
Linear search.
Yeah, linear search. So just now we discussed, right? Okay, so in this, while discussing about best case, average case, and worst case, so if there are 1 lakh elements, you have to search for the entire set of elements. So that is called linear search. Searching one element one by one. Okay, searching the elements one by one is called linear search. Okay, if there are 1 lakh elements, the worst case is going to be 1 lakh, right? If there are 2 lakh elements, the worst case is going to be 2 lakhs. So that is why it is order of n, linear search. Okay, so I have a question in the chat box, Mala. So how is the complexity of sum of natural numbers order of 1? I still didn't get it. Okay, anyone wants to answer for this question? Just now I gave you the answer.
So because it can be solved by direct formulas.
So it has a direct formula, right?
Yes.
N into n plus 1 by 2. That's a direct formula. So whatever might be the value of n, okay, you can use this formula to calculate sum of n natural numbers. That's why it is order of n. Okay. So the next higher complexity is order of n log n. Okay, any example for n log n?
Merge this out.
Yeah. Merge sort. So this sorting algorithm also we'll be discussing in the next 2 classes. Okay, next class we'll discuss about binary search and all. And the next class, after that class, we'll be discussing about merge sort. Okay. And then order of n square. N to the power 2. Yes, any example for order of n square algorithm?
Pick or bubble
Quick-
sort also.
Yeah, okay. Quicksort, yeah, okay. Quicksort worst case is also n square. But
Bubble
still, we
sort.
have simpler algorithms, bubble sort, insertion, selection. So these 3 sorting algorithms also takes n square complexity, time complexity. Okay. Okay, so to generalize this, we have order of n to the power a constant value. Let's say it is k. Okay, so just a general form. See, all these things are polynomial terms. Okay, all these things are polynomial terms. Now, next is we have n factorial. Okay, and then e to the power n. Okay, and then n to the power n. So all these are non-polynomial terms. Okay, so why these are like a non-polynomial terms is that like so if n increases, okay, so there's a drastic change in, okay, log n is also not, see, like if you see the curve, it will be a smooth curve which is decreasing curve. That's why it comes under log n comes under polynomial. Okay, actually log n is not polynomial, but still it is considered in this set. Okay. Okay. So these are non-polynomial terms. So if there's a small increase in n also, there will be a drastic change in these terms, right? So if n is 5, if n factorial is going to be 120. Okay, if n is 6, it is 720. Okay, 10 factorial, okay, it is a very huge number, right? Okay, even that's a small change in value of n, the output is going to be very large. That's why these are all non-polynomial terms. Okay. Okay. So next we'll see about complexity reduction. So we have understood what are different types of complexities. Okay. Mostly we'll be revolving around this only in the first few classes. The last two classes we'll see few algorithms which takes non-polynomial algorithm. Okay. So now next we will see complexity reduction. So we'll take a very simple example to understand this complexity reduction. Prime numbers. Okay. So what is the definition of a prime number?
Divisible by the number and one.
Divisible by the number and one.
Number itself and one.
Number itself and okay. What about one?
One and itself.
A number
No,
that
no.
is exactly two divisors.
Yeah. Very good. So prime number is a number which has exactly two divisors. Okay. And before that, most important thing is prime number should be a natural number. So it works only for natural numbers. We cannot tell whether any negative number is a prime number or not. There is no argument at all for that. Okay, it doesn't come under this category at all. The first constraint is it should be a natural number, and then it should have exactly two divisors. Okay, so if you take one is a natural number, but whereas this second rule is not satisfied, right? So that is why one is not a prime number. Okay, but still we cannot say it is a composite number. So what is a composite number?
A number that has more than two divisors.
Yeah. So again, it should be a natural number and it should have more than two divisors. Okay, so one has only one divisor. So it doesn't come under any of these two, right? But still it is a natural number. So we have to comment whether it is prime or not. That's why it is neither prime nor composite. Okay, for negative numbers, okay, we should not consider whether it is prime or composite at all because it's not a natural number. Okay, fine. So now what is the logic to find whether a given number is prime or not with respect to programming? So if you take any number, it is going to be divisible by 1, right? Okay, so we need not check whether the number is divisible by 1 or not, because we definitely know that it is divisible by 1, and we also know that that number will divide itself, right? So again, we did not check whether that number is dividing itself or not. So unnecessarily, we did not do two operations. One is dividing the number by 1, and other is dividing the number by itself, because we know the result already. It is going to divide. Okay. So now what we'll do is we'll just put a loop that will run from 2 to n minus 1. Okay, it is the start of the algorithm. Okay, so we're going to reduce this algorithm step by step. So as of now, let us say we have written an algorithm which will run from 2 to n minus 1. Okay, you have put a for loop and the range is 2 comma, I'll put n because n value is not inclusive, right? So 2 to n. So what would be the inner logic? When do we say that it is not a prime number?
Remainder should not be 0.
Yeah. So any number between this range, okay, 2 to n, 2 to n minus 1 actually, if it is dividing the value n, then it is not a prime number, right? Suppose this particular loop is in a function, okay? So if n mod I is equal to 0, okay, return false. Okay, so now this loop keeps on running. So when do we know that it is a prime number? If none of the numbers are dividing it, right? So between 2 and n minus 1, if none of the numbers are dividing, then we'll know that it is a prime number. So what you will do? So we have an else for loop, right? I think you remember this. This else is for the for loop. Okay, when will this else get executed? If this entire range gets executed, then this else will get executed. Okay, I hope you remember this. So if it comes to the else part, then you have to return true. Okay. Yeah. So now what is the complexity of this algorithm? For any particular value of n, how many times, what is the maximum? Okay, we have to tell the worst case, right? So what's the maximum number of times the loop runs?
I think it's n minus 2.
N minus 2. Yeah, very good. So the complexity is n minus 2. Okay. Now, so let us try to reduce this n minus 2. Now, the next constraint which you're going to take is, so like if you take any number, so is there any number between n by 2 and the number minus 1, okay? N by 2 and the number minus 1, which will divide that number. Okay, to be more clear, take number 20. Okay, so what is 20 by 2? It is 10. Okay, so the next number to 10 is 11. So is there any number from 11 to 19 which divides 20?
No.
No, right? So it holds for all the numbers, right? Even if you take 100, from 51 to 99, there are no numbers that will divide 100. Okay, so but we know that none of the numbers are going to divide, but still we go till the end, right? So we can reduce that calculation as well. So now how to change the for loop? What should be the range? Two comma,
N by 2.
yeah, n by 2 plus 1. Why? Because not inclusive, right? That's why. So 20 by 2 is 10. Okay, so what I give is I give 11. Why? Because 10 also should be included. Okay, that's why I given plus 1 here. And this is a float division. Okay, just to avoid floating numbers. And the same logic. Okay. Any doubts in this? Anyone? Understood, right? So what is the complexity of this algorithm? Yes.
N by 2
n by 2
minus
minus
1.
1.
Yeah, very good. So n by 2 minus 1. So it is nothing but we are just reducing this entire data, whatever data set we had, data set in the sense like numbers we had by 2. So it is also, we can also write as n minus 2 by 2. Both are same. Okay, n by 2 minus 1 or n minus 2 by 2 is also both the same. Okay. So now we have reduced by half. Now let us see we are able to reduce it further. Now we know that all the prime numbers except 2 are odd numbers, right? All the prime numbers except 2 are odd numbers. Okay, so for odd numbers, is it necessary to check whether an even number is dividing an odd number?
It's not.
No, right? So we need not check whether a even number is dividing an odd number or not. Definitely, an even number is not going to divide an odd number. Okay, for example, you take 11. Okay, so 2, 4, 6, 8, 10. So all these numbers are even numbers. They're not going to divide them at all. So we can just skip all the even numbers, okay, except for 2. So because 2 is a special case. So now I'll just write if n is equal to 2, return true, and then I'll put the for loop, and then what should be the range? So from which number should I start from?
3. You should start from
3.
3.
Yeah,
Three.
should start from 3 because 3 is the first odd number which you're going to consider. 3, and the end value is the same till by 2 elements. Okay, colon, and then the same logic.
So we need not to include any step size.
We need not include any.
Step size. I mean, by 2.
I didn't get you.
No, we need. You said that 11 cannot be divided by 4, 6, 8, 10 now.
Yeah. Yeah. Correct.
So,
Step size needed. Sorry. Correct. So you started from 3. So next we should go, if you take only the odd numbers, right? So next you have to go to 5, then 7. Okay, like that you have to jump. So for that, the step size should be 2. Okay. So now what is the complexity of this algorithm?
I think it has been hovered -1.
Sorry?
I think
didn't
it
get
has
you.
been hovered and -1. We have subtracted 1 from the left end, and we have also reduced the number of steps to half.
Yeah. So like what is the final output?
I think it should
Fine.
be n minus 2 by 4 minus 1.
Okay, fine. No, it is just n minus 2 by 4.
Okay.
so can you explain it again?
Yeah. So why? Because see, from this previous set of values, we are removing all the even numbers. That's it. Right?
Okay.
Okay.
It's this way.
Yeah. So we can go one step further. So it is not that you should go till n by 2. By research, it has been proved that it is enough that you go till the square root of n.
Square root.
Okay, it is still reduced. But the thing is, calculating square root will also involve some calculation. Okay, so that's a function to calculate square root, but that doesn't operate in constant time, right? It again takes some more time. So it is enough that you stop here itself. Okay, so we started with order of n minus 2. Okay, then we further reduced it to n minus 2 by 2. And now we reached n minus 2 whole divided by 2. So if you have the square roots and all stored in a particular location, if you're able to use that in a constant time, then you can go further by reducing this, changing this to square root of n. That's it. Okay, at that time, what happens? It will become square root of n divided by 2. That will be the complexity. Okay, fine. So shall we see one more example for complexity reduction? Okay. So now we'll also see the space also would get reduced. Okay, I'll give an example where the space is also being reduced. So now the problem is, so you'll be given the string. Okay, input is a string. Okay, and the logic what you are going to perform is tell whether all the characters are unique. Okay, the output is just yes or no. If all the characters are unique in the string, then you should print yes, else you should print a no. That's it. Okay. You can take any string. For simplicity, let us take a like easily understandable strings. So if the input is this, okay, so what happens here? You can see that C is repeating, whereas all other characters are not repeating. So even there is one character which is repeating, then the output should be no. Okay, so this for this the output is no. For this the output is yes. Okay, so all the characters are unique. Okay, so now can you tell me a order of n square algorithm to solve this problem? You have to check whether all the characters are unique. So I want an n square algorithm. Yes. Question is clear, right? A string would be given. You should give the output whether all the characters are unique. Okay. See, actually very simple. You take the first character, compare with all the other characters. Okay. So if there is any repeating in this character, then you can directly print no. Else you proceed with the next character. You take C, compare with all the characters. Now you can see C is repeating over here, so you can print a no. Okay, so come here in the second like example. So we have B, compare with all the characters. It's not repeating anywhere. Then C, not repeating anywhere. D, E, F, G. Okay, so like this algorithm is actually order of n square algorithm. Understood this? You take B, compare with all the characters. Take C, compare with all the characters. Take D, compare with all the characters.
Why it is n square? Can you explain this?
Okay, fine. Very simple calculation. See, how suppose what is the length of the string?
It's n.
6, 7, right? Okay,
It's 7.
7.
length is 7. So how many comparisons would you make
Plus
for
5.
B?
Plus 3.
6.
How many comparisons would you make
6.
for B? 6 comparisons, right?
Hmm.
And for C,
5.
yeah, 5 comparisons. Okay, and for D, 5 comparisons, right? If you take C, compare all the characters because B you already considered. So you know that B
Done
is not
already.
first. Okay, so you'll not consider B again while taking C. Now for D, be 4.
4.
Okay, like that it goes on. Then 3, then 2, then 1. Okay, so what is this?
This is sum of 6 natural numbers.
Yeah, that is sum of, if length is considered as n, so sum of
And
n
minus 1 natural
minus 1 natural numbers. Okay, so what is the formula for n minus 1 natural numbers? Sum of n minus 1 natural numbers.
That's n minus 1 by 2.
Yeah, so sum of n natural numbers formula is n into n plus 1 by 2. Sum of n minus 1 natural numbers is n into n minus 1 divided by 2. Okay, so if you just multiply it inside, you'll get n square minus n whole divided by 2. Okay, if you take 2 inside, you'll get 2 n, sorry, by 2, right? Okay, it will be whole divided by 2. See, okay, so that is a like a simple rule in
Square
complexity
term. Okay.
analysis. Yeah. So if we have a polynomial term like this, you should consider the highest polynomial with the degree. Okay. So now the lower polynomial terms will get removed. Why you are doing this is like always the complexity will be calculated for a very large number. Okay. So suppose n is 1 lakh. Okay. So suppose n is equal to 1 lakh. 1 lakh means what? 100,000. Okay. So what is 100,000 whole square? 1 followed by
10 zeros.
10 zeros. Okay. So comparing with this 1 followed by 10 zeros, this 1 lakh is very negligible, right? Okay. So that is why we will eliminate all the lower order terms. Only the highest order term will be taken. And so even though this coefficient plays a big role, we will not be considering coefficients because we are just finding out what is the order of the algorithm. Okay. So whether it is n square or whether it is n or log n. So that is what we are interested on. Okay. So like, um, so that's why this is the rule actually. Okay. So we have to remove the coefficients and the lower order polynomials. Okay. So that's why it is n square algorithm.
Okay, sir. Thank you.
Now, so like, is it possible to reduce the complexity of this algorithm if a few additional spaces are taken? That is taking some additional memory. Can we reduce the algorithm complexity of the algorithm? Now it is n square. Can we reduce it to order of n?
So we did a similar question by converting this into a list.
Hmm.
So
After
then
converting
we,
to a list?
and then we can check whether the first element is present in the list. So it's yes.
Again, if you, what is the function used to check whether it's present or it's not? In, right?
Yes, sir.
That is also a comparison, right?
Okay, okay. Yes. Same thing. Similar thing.
Yeah. Okay. So now to further reduce it, I told you that they can use some additional spaces, right? So for that, instead of additional space, I'm just going to use flag values. Okay, flag values means if B is occurring, I'll just mark the flag for B as 1. That is, it has occurred. Then if C has occurred, I'll mark C as occurred by marking the flag for C as 1. Okay, so what I would do is, 1 minute, let me open the Excel sheet. Yeah. Is my screen visible? Hello?
Yes, sir.
No, sir.
Now is it visible?
Yes, sir.
So now what we will do is we'll just consider flag values. Okay. So flag value is nothing but I'm going to take a list of 20, suppose that there are only alphabets. Okay. And then all are capital case. Okay. Uppercase characters are there. So how many uppercase characters are there totally? 26 uppercase characters are there, right? A to Z. So I'll just create a flag. So let's suppose there are 26 characters. Okay. So now what I would do is I would make this as a flag value for A. Okay, and this for B, and this for C, like that continuously. So this is a flag value for A, and this for B, this for C. Okay. Now, initially I will mark it 0. So I have not processed any of the characters. So I will mark all the values as zeros. Okay. So whenever a particular character is occurring, I'll just mark that particular value as 1, which corresponds to that character. Understood? So here, if you see, first B is occurring, right? So I'll first check whether B has occurred or not earlier. So no, it has not occurred earlier. So I'll mark this as 1. Next, C. C has also not occurred earlier. So I'll mark this as 1. And D, okay, not occurred, I'll mark it as 1. Next is A, not occurred, I'll mark it as 1. Now it is C, right? So if I see in the place of C, it is already 1, which means C has already occurred. Now I can return false, right? Return no. So understood? So this algorithm, what happens? It will just iterate only once the entire set of characters. So what is the complexity if it just iterate only once for the entire set of characters?
I think it's n.
It's n, right? So if length is n, then the order is also n. Understood, everyone? Any doubts in this? I just have an additional memory of 26, okay, and then each value would be marked as 0, okay, and then I would just mark it 1 if that particular character occurs. And every time I mark, before marking 1, I would check whether it's already marked 1 or not. So if it is already marked 1, then it means it has occurred earlier. So I'll return false or no, whatever. So this is the logic. And since it is checking only once all the characters, okay, that's why it is order of n. Now the third reduction, what we can do is, so we have the bitwise operators, right? So bitwise operators are really like reduces the complexity by a huge amount of time. Okay, so while taking the operators class, okay, so at that time also I gave an example, right? Bitwise operators. So do you remember what example I gave you for left shift, right shift shortcut? So what is the equivalent operation for A right shift n? Yes,
2 power minus a.
2 power minus A.
I mean
No.
1 by 2. 1 by 2 power n.
Where is
I-
where's the A?
5 into 2 to the power of n.
Sorry, I into.
5.
Okay, here A, right? A into. No, it is right shift. Okay, fine. For left shift is A into. For right shift is A divided by. Okay. So 2 to the power of n. That is with respect to Python is 2 double star. Okay, so here this particular calculation is way too costly than this constant time, right? So here you have to calculate the power and then you have to divide that number by, sorry, A divided by that number, whatever you get. Instead, just do a right shift by n. So this bitwise operators will, like you have to think about bitwise operators a lot because it will reduce the complexity by a lot. We'll see how it is reducing here. Here it will reduce the memory. Okay, fine. So here you can see that for these 26 characters, we are using like every character, there's like only one change, right? Either it would be 0 or it's going to be 1. Either 0 or 1 is going to be the value. So for that, why should we waste the whole integer? Right? Suppose the integer is taking 4 bytes of memory. Okay, just to mark it 1 or 0, we will not waste that whole 4 bytes of memory, right? So 4 bytes means how many bits?
32.
Yeah. 32 bits, right? So we're just going to set it as 1 or 0. So for that, we need not have 32 bits. 1 bit is enough for that, right? So that is what we're going to do now. So let us consider an 8-bit integer, okay, for simplicity. 0th bit, first bit, second bit, till 7th bit. And let us take the same example, this one itself. Okay, so let us take this variable as v, okay, or make it as flag, okay. So this is going to represent whether a particular character has occurred or not. So initially, how to mark this variable as 0? It's a single integer, okay? Don't think that it's a list. It's not a list. It's a single integer. We are just represented it as a single byte. That's it. Okay, there are 8 bits inside this integer. Let us consider that. So how to make this all these bits as 0? What should I initialize f with? Yes, what should I initialize f with so that all the bits become 0? Yeah, very
0.
good. So f is equal to 0. So what happens? The entire bits will get 0, which means that none of the characters have occurred still now. Okay. Now next is I will have a temporary variable t, okay, which is going to represent the current character. Suppose I'm processing b, then I will represent b in t. Okay, so which bit corresponds to b? Which bit number corresponds to b? Starting from 0.
0.
0 corresponds to a, 1 corresponds to b, 2 corresponds to c, like that goes on. Okay, so I'll just mark it here. A, B, C. Fine. So now, so I'm considering the first character B. Okay. So now, which bit of T should be marked as 1 to represent B?
One.
Yeah.
1 place.
Bit number 1 should be marked as 1. Okay. Now, what I do is I initialize T with 1. Okay. And after that, we'll do some operation to make it represent B. Okay. So if I initialize T with 1, okay, which bit will be marked as 1 now? 0th bit, right?
Yes.
Okay. So are you able to follow anyone? If you have doubts, you can stop me anytime. Not at all an issue. Okay. So I initialize T with 1. So what happens? 0th bit is 1 now. So now what operation should I perform to make T represent B? Which means 1 should go to the first position. Now currently it is at 0th position. I should move it to first position. So what should I do?
Left shift.
Yeah, very good. So I should left shift by how many times?
1 time.
1 time. Okay. If it was D, then how many times should I left shift?
And 3.
3 times. Yeah. So based on the character, we're going to left shift those many number of times. So now the thing is how to calculate how many number of times I should shift. The only general way, right? We cannot write 26 if conditions. So if it is A, then how many times should I left shift?
None.
None, 0 times, right? So if it is B once, if it's C twice. So
That
now
means
the
n
starting,
minus 1.
no, the starting point is A, right? Okay, so for every character, there is an ASCII value corresponding to it. So we can make use of the ASCII value. So how to take the ASCII value of a particular character? Which function do we have to take the ASCII
Order.
value?
Order.
Yeah, order. ORD function is there. Now what we do is first we will take the ASCII value ORD of, let's suppose we have taken that B, okay? ORD of B minus ORD of A. Okay, so this actually should be a variable, okay? Why? Because it corresponds to each and every character. Next time this should be C. Next time it should be D, like that. And this is the same order of A. Now these many, excuse me. So these many number of times we have to do a left shift. Okay, so T equal to T left shift this one. Understood this logic, right? So now the first character is B. So order of B minus order of A. Order of A is 65. Order of B is 66. So 66 minus 65 is 1. So T left shift 1. So now what will happen to T? Will get shifted by 1 position. This would be the output of T left shift 1. Okay, so now we made T represent B, the first character. Now the task is you have to check whether this B is already present in F or not. If not, you have to make the corresponding location as 1 without affecting the rest of the characters, rest of the locations. Okay, so else we can print that it is not unique. Are you able to get it? I'll repeat again. Now we have made T represent B. Now the next task is you have to check whether this particular character is already present in flag or not. Okay, if it is not present, you have to mark the corresponding location to 1 without affecting the rest of the positions. If it is already present, then I have to return false, which means not unique. Got it? Okay. So first we need to check whether the corresponding location is set or not. So which operation can I use? Yes, the corresponding location, I want to check whether it is set or not. You just like imagine and see. If it is already set and if I perform some operation, what would happen? No, it is not set. Okay, I'll give a clue. We have to use some bitwise operation. Which bitwise operation should I use? Okay, I'll tell the bitwise operation also. You tell me the logic. Okay, so we have to use AND operator, bitwise AND operator. Yes.
Zero and with 1 becomes 0. If 1 is present in the V, then it becomes 1.
Okay. So what is the statement? Okay, so actually, like suppose if this value is also 1, if I perform AND operation, F and T, F and T, okay, F bitwise and T. So what would be the output? Output can be any value other than 0, right? It can be any value. So if this number is set and this is also set, then it will be a different value, right? This number is set, this number is also set. Okay, then it will be a different value. Understood? If both A's are present, then it will be a different value. This will be 1. Now it will be 2, right? Understood? So if F and T, like if you are getting a non-zero value, what does it mean? It means the corresponding location is already set. Okay, so if we have any other variables, any other characters which are present, but this character is not present. So what is the output that you will get if you put F and F single, F bitwise and T?
0.
0, right? So whatever might be the set characters, okay? But if this corresponding bit is not set, then you will get the value as 0. So this is the logic. So if you get a non-zero value, it means that the particular location is already filled. Any doubts in this? Anyone? Understood, right? Okay. So the condition is if F and T is not equal to 0, you will directly straight away return false. Okay, else what would you do? Now we have found that the corresponding character is not present. Now I want to make this particular character to be set here also. Now which operator do you use?
Or
Yeah, very good. Okay, so without affecting the other characters, we want to make this particular character alone to be set. Means you have to use an OR operation. Okay,
F is
else,
equal to F or T.
yeah, F is equal to F bitwise or
Or
T. Now what happens? This corresponding location will be set here also, which means that B has occurred. Understood? So now you will iterate this for the entire loop, entire characters. Okay, then finally, if none of the if it is not breaking in between, then you will return true. That's all. So did all of you understand? Any doubts in this? So here, can you comment about the complexity? What is the time complexity for this algorithm? It is order of n, right? Yes. So it is iterating over this entire set of characters once. So it's order of n. Okay. So here inside the for loop there are some additional operations. Okay, but still it is order of n only. And talking with respect to space, in the previous example, okay, previous example also it was order of n only, but it was taking a lot of space, right? So 26 characters we are using. So 26 integers we are using. Whereas here it is done with a single integer. So this algorithm is like optimal with respect to time as well as space. Any doubts? Yes, why you people are silent?
No, sir.
Okay. Others?
Yes, sir, understood, but it's little complex.
Yeah. So if you work out for, if you take a string and then work it out, then it'll be, you'll understand it better. Yeah. Okay, fine. So the next important thing you're going to see is time space trade-off. So time space trade-off. So like, what do you think would be this time space trade-off? Any guess or any idea about this? Trade-off, right? So I think you know you're familiar with the term trade-off. Okay, fine. I'll tell you. So if you want a certain algorithm to perform well with respect to time, then you have to compensate with space. Okay, and if you want an algorithm to perform well with respect to space, then you have to compensate with respect to time. That's it. This is time space trade-off. Okay. So the best example for time space trade-off is the swapping algorithm. So in swapping, you know what is swapping, right? Suppose you have the value, two variables A and B. So the values of A and B should be swapped, right? A's value should go to B and B's value should go to A. Now for that, there are, so the first way is with using a temporary variable. Okay, with using a temporary variable, how do you swap two variables? Suppose there are two variables A comma B. So in Python, it is very simple. If you put A comma B equal to B comma A, you'll get swapped. Okay, but internal what is the logic we should understand, right? So but still. So using temporary variable, what is the logic for swapping two numbers? Let the temporary variable be T. Yeah. T is equal to
B.
first A. Okay, you can
Okay.
take B also, no problem.
A is equal to B. B is equal to T.
Yeah. So A is equal to B and then B is equal to T. Right? So suppose if A is equal to 5, and B is equal to 10. Okay, now here what happens? The value of T becomes 5, right? So T is equal to A. So now T's value is 5. Now, since you have stored A in T, now A becomes free now. Okay, you can store some value in it. So what you're doing is just taking the value of B and putting it in A. So A becomes 10. Okay, after doing this step. Now after that, we have copied the value of B in A. So now we can take the value of T and store it in B. So now B becomes 5. Okay, so now A is 10 and then B is 5. So it got swapped. Now without using temporary variable,
Addition and subtraction.
yeah, you have to use addition subtraction operations. A is equal to A plus B.
B is equal to A minus B.
Yeah, B is equal to A minus B. And again,
A equal to
A is equal to, again, A minus B only. Okay. So now what happens here? What is a plus b? Now the value of a is 15, right? So a plus b. Now I stored the value of a in b. Now value of b is what? B is equal to a minus b. Now the value of a is 15 minus 10 is 5. Okay, so b is equal to 5. 15 minus 10, 5. A is equal to a minus b. A is 15 minus, now the current value of b is 5, right? Okay, earlier it was 10, now it has become 5. So 15 minus 5 is 10. It got swapped, right? So this is the way in which you will do using a temporary variable, and this is without using temporary variable. Now let us come on with respect to space and time. So the first algorithm, how much memory it takes, just the number of variables. This, how many variables are there?
3.
3. And how much time it takes? We just assuming all the operations take 1 unit of time. So here assignment operation is there, and here assignment and arithmetic operations are there. So here 3
Yeah,
assignment
3.
operations. Okay, so 3 units of time. And coming here, how much memory it takes?
2.
2 variables.
Only 2 variables, so 2 memory spaces. And time?
6.
6. 3 assignment, 3 arithmetic, to total 6. So this is time space trade-off. Okay. So here we have an efficient algorithm with respect to time. Here we have an efficient algorithm with respect to space. Okay. So we can also look at in another angle. Okay. So here the time is 6, whereas here the time is only 3. Just by increasing a single memory, we are able to reduce the time by half. Okay. So this is like a way. This is
Better.
like how to say this is like
Better.
yeah, this is better. And so if you see in algorithms, okay, so we have a concept called dynamic programming. So in dynamic programming, most of the time we'll be using this time space trade-off only. Okay, while coming to dynamic programming, I'll explain much more clearly. So this is time space trade-off. And I can give you one more example. Yeah, so I'll use the Excel sheet to explain this. So I think I explained you the Fibonacci series using recursion by using Excel sheet only, right? So for calculating Fibonacci of 5, yeah, so what we should calculate? We should calculate. We should know Fibonacci of 4 and Fibonacci of 3. Right? Only if we know these two, we will be able to calculate Fibonacci of 5. And for again Fibonacci of 4, we should know what is Fibonacci of 3, Fibonacci of 2. And 3, f of 2 and f of 1, f of 1 and f of 0. And here, f of 1, f of 0. Fine. So this is how the Fibonacci tree looks like. Now what we're going to do is, see, you can see a lot of redundant operations happening. So f of 3 is already calculated, but still again, the entire structure repeats, right? And f of 2 is also already calculated, and it is repeating 3 times. So instead of doing these repeated calculations, what we can do is, we can simply store these values in a space. Okay, and just mark it as 0, 1. So what I would do is I'll just mark them with a value which is not a Fibonacci number. Okay, so 0 is a Fibonacci number, so I'll not be initializing all these values as Fibonacci as 0. Instead, I'll just mark it as -1. So which means that Fibonacci number for that particular index is not yet calculated. Understood? And I'll initialize 0 and 1 because we already know that f of 0 and f of 1 are known values. Okay, 0 and 1. So now what happens is every time instead of calculating it newly, it will just refer to the table whether it is already present or not. If it is already present, it will directly take that value and return it to the previous function. Okay, if it is not present, then it will proceed further to the next recursive calls. So let us do it from the first. F of 5, it will check whether 5 is already calculated or not. No, it is not calculated. So what happens? It will do a recursive call to f of 4 and f of 3. So first it will make a recursive call to f of 4. Till then f of 3 will be idle. Okay. So now f of 4, it will again check whether it is calculated or not. No, it is not calculated. So it will produce two recursive calls. Okay, f of 2 will be idle. F of 3 will be called. F of 3 again not calculated. So go to f of 2. It is also not calculated. So I go to f of 1. F of 1 is already calculated. So it will return 1. Okay, f of 0 is already calculated. So it will return 0. Now what happens here is it will calculate f of 2 by adding 1 and 2, 1 and 0. So it will calculate before returning to the previous function. It will just update that value over here. And after that, it will return 1 to the previous function. Now it will come to the right, f of 1. It's already calculated, so return 1. Now it will calculate the value. 1 plus 1 is 2. So before returning 2, it has to update this table and then it will return 2. Now, once it comes to f of 2, what happens? It will refer the table. It is already calculated. So instead of producing these two recursive calls, so it will directly return 1. So 2 plus 1 is 3. So before returning, update the value of 4 as 3 and then it will return. Now coming to the right hand side, f of 3 also is already calculated. So return 2. Now all these functions will not be called at all. Understood? So just for f of 5, see how many functions we have omitted. So imagine a tree for Fibonacci of 100. Okay, so we'll be reducing so many calculations. So just by like involving some additional amount of memory, we're able to reduce so many calculations. So this is also a good example for time-space trade-off. Okay. So now let us see the various algorithmic strategies which is going to be the next few sessions. Okay. So there are different algorithmic strategies. So basically what you have to do is the first algorithmic strategy which you're going to perform is mathematical formulation. So whenever a problem is given, you check whether that can be solved using any mathematical formula. So if you're able to like produce a mathematical formula for a logic, then it can be solved within a constant time. Okay. So if you're participating in any competitive exams, this will be very, very helpful. Okay. Instead of thinking with respect to loop, okay, if you think with respect to mathematical formulas, so what happens? Your logic also will be very simple. Okay. Time also will be very less compared to iterative algorithms. So the first thing is you have to check whether you're able to solve using mathematical formula. So if that is not working out, then you have to go for any of these 5 strategies. Okay. The first strategy is divide and conquer. Next is greedy, dynamic programming, backtracking, branch and bound. Okay. So if even if none of these strategies are working out, then only you have to go for brute force method. Okay. So but what we will do, we will leave all these strategies and directly we'll go to brute force method. Right? That is what we do, right? Okay. But so this is the procedure. First, you have to check whether any mathematical formulation is possible. Else, you have to check for these strategies whether you are able to convert the problem into these strategies. If not, then you should go for brute force method. Okay, fine.
So these strategies are supposed to be checked one linearly, like if divide and conquer doesn't happen, then greedy, then dynamic, like this, or any of
No,
them.
no, that is you have to think and see. You cannot do it with respect to programming.
Okay, okay.
Okay, so let us discuss a few problems. See, we are going to see about these algorithms only in the future classes. Okay. Um, okay. So given a number, okay, it can be any number n. You should check whether it is a power of 2 or not. Now you can tell your ideas. Output is yes or no. That's all. Any number would be given. You should just check whether it is a power of 2 or not. Is anyone?
Possible to convert it into this binary to be easy.
Okay.
There will be singles one and the rest of them will be zeros.
Okay. That would be a single one and rest of them would be zeros. Okay, fine. So what is the complexity of the algorithm? Okay, so what he says is like suppose the n is 64. Let us see some powers of 2. Okay, simple powers of 2 first. So 2. So the binary value of 2 is okay. Let us come to this later. Let us discuss the other possible ways. Any other ways without using binary?
Bitwise operators.
Bitwise operators.
You
Okay,
just-
tell me without bitwise operators. Tell me. We'll come to bitwise operators later. What's the
I
normal
think we
logic?
check at each stage. We should see whether this is divided by 2, and once we divide it by 2, the quotient should be divisible by 2 at each stage.
Okay. So like what would be the stopping point? When would you stop this procedure?
When we finally get a 1,
Yeah, very good.
keep dividing it by 2.
Yeah. So you keep dividing it by 2. Once you reach 1, okay, and none of the numbers in between are giving a remainder, then it is a power of 2. Okay, so what is the complexity of that algorithm? Suppose you take 64. The next step it becomes 32.
It will take
Next
6.
step becomes 16. Becomes 8. 4 into 1. Okay. So this is also an example for log n complexity, right? If you take 70, Okay, 70 divided by 2 is 35. And again, if you divide by 2, it will not give a remainder 0. So you can stop here itself, telling that it is not a power of 2. Okay, so if you take any power of 2, this will be satisfied. Okay, at last it will reach 1, and none of the numbers in between would give a remainder. Okay, all the numbers in between would be divisible by 2. Fine, this is the normal logic. Okay, so now coming to bitwise logic. Yeah, now you can tell me the bitwise logic. If you see all the
I think
powers of
By 1, right shift by 1.
okay, so if you see all the powers of 2, so 1 is a power of 2, right? 2 power 0 is 1. Let us take the 8-bit representation. Okay, 2 is also a power of 2. Okay, and then 4, 8, 16. All the powers of 2, you can see that are having exactly 1%. So can we have this as the logic to find out, or is there any other procedure? Is this a clue to find out whether it's a power of 2? I'll give you a much more simpler way. And Abhishek, you told something with respect to shift right.
Yes, sir.
Shift right is equivalent to this only. Shift right is nothing but dividing by 2, right?
Yeah.
Okay, shifting right or dividing by 2, both are same. So shifting right and like dividing by 2, both the same algorithms only. It will also take log n time. Okay, so you can do that also, not a problem. So after doing a shift right, what would you do?
And with 1 second, sir.
After doing shift right, again you have to do a modulo with 2, right? No, if you do a shift right, what happens is you will not the last value which is present would get like discarded, right? Okay, you can think about it. Any other logic? So there is a better logic in bitwise operator itself. Okay, I'll tell you. So you take any of these numbers. Okay, so these numbers are going to be the starting point for this particular series, right? Is a starting point for the 5th bit. 8 is a starting point for 4th bit. 4 is a starting point of 3rd bit. Got it? All the numbers less than 16, okay, will not have this particular bit as 1. Got it? So it will just revolving around these values only, these 4 zeros only, these 4 bits only. But this particular bit will not be set for any of the numbers less than 16. And this is the same for all these cases. Okay. So now
Yeah,
we're going to make use of that property. So what is that is n minus okay, n, and okay, so let us take n minus 1 for all the numbers. Okay, and then if you see n minus 1 for all the numbers, you can see that all the ones would be set. Sorry, all the bits would be set as 1. Got it? See, for
Yes,
3,
sir.
these 2 bits will be 1, right? And for 7, all these 3 bits will be 1. And for 15, all these bits would be 1. Okay. So n minus 1, if you do an AND operation, n and n minus 1. Okay. So what value will you get? If it's the power of 2, yes. If it's the power of 2, what is n bitwise and n minus 1? Hello?
0.
Yeah,
0, 0.
0 only, right? Okay, so if it's the power of 2, n and n minus 1 will always be 0. Okay, this is for power of 2. Now we have to check for other numbers also. So if any other number other than power of 2 will produce, if it produces this, we cannot like use this as the logic for finding whether it's a power of 2 or not, right? Okay, so let us check for few other numbers. So if you take any other number, suppose you take 15. Okay, so 15 minus 1 is what? 14, right? So 15 minus, sorry, 15 minus 1 is 14. So 15 and 14. Okay, so if we take the adjacent numbers, except for the power of 2, all other values will have the same, the last bit would be set. Yes or no? Yes, what is for 15? 0, 0, 0, 0, 1, 1, 1, 1. And for 14? 0, 0, 0, 0, 1, 1, 1, 0. You take, consider any number and see, this last bit would be set as 1 for adjacent numbers, except for the power of 2. Okay, so only for n, if n is the power of 2, this particular expression would give us 0. Fine. So this is the best algorithm, right? Constant time, whatever might be the number, you just perform an AND operation with a number less than one number less than that number. If you get 0, then it is a power of 2. Else it is not a power of 2. Understood this? Hello.
Yes, sir.
Okay. Others?
Yes, sir.
Yes, no.
Okay. So these are all complexity reduction. Okay. So we'll see one more problem. I think this is very easy and I think you will answer this. See, suppose you have a list, okay? And this list is containing only 0, 1, and 2. No other numbers are there. 0, 1, 2. Only these 3 numbers are there. And I want you people to sort this entire list in ascending order. Okay. So it 0, 0, 1, 2, 2, 2. I don't know how many numbers are there. Can be any number of numbers and in any combination.
Without built-in function, sir.
No, yeah, without built-in function. If you're using built-in function, then you have to tell me the complexity of that built-in function. So any idea, anyone?
assigning minimum value to the 0th location and then comparing with the adjacent. If it's maximum then adjacent, then we need to swap them.
Assigning minimum value to
0th location and then comparing it with the adjacent location.
minimum value means which value?
Like min is equal to a of 0, like just taking a variable, sir, minimum variable.
Some value minimum or any
no.
minimum value from this?
Like m is equal to a of 0, then compare it with the adjacent variable, adjacent location.
Okay, comparing min with adjacent variables. Okay.
Yeah, for loop.
Then
If it found to be maximum, then adjacent, then swap.
okay, it is like bubble sort.
Yeah. Yes,
But
sir.
bubble sort complex is n square, right?
Okay.
No, see, it is not normal sorting for sure. So you can think about different methods. So actually it's very simple. If I tell the logic, then okay, fine. I'll give you a hint. It involves counting.
It's a 3 power n.
Sorry? 3 power n? No, what is 3 power n? The question is, you have to sort these elements in ascending order.
Ascending order.
I didn't get you. Sorry.
I basically didn't get the question. Maybe I answered the wrong question.
Okay. Okay, so actually it's very simple. You take 3 variables. One variable to count the number of zeros. Other variable to count number of ones and number of twos. Okay, so you check every variable. If it is 0, increase the count of 0 by 1. So initialize all the values with 0. And what you do is, you will have an if condition. Okay. So if it is 0, increase the value of 0 by 1. If it is a 1, increase the value of 1 by 1. If it is 2, increase the value of 2 by 1. Understood? By this way, you can find out how many zeros are there, how many ones are there, and how many twos are there. That's it. Okay. So how many zeros are there? 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros are there. So after the iteration, the number of zeros count would be 9. The number of ones is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And number of twos 1, 2, 3, 4, 5, 6, 7, 8, 9. So now we have counted the number of zeros, number of ones, and number of twos. Now what you do is just iterate, just put a for loop for 0 number of times and then keep printing those many number of zeros. Okay. So just put 3 more for loops for I in range of zeros.
Can we use insert method?
Insert?
Insert of 0 into 9. I mean, list of 0 into 9.
That again involves a loop inside it. So
Okay.
L is equal to empty list. Just put L dot append. Or, okay. In Python, to make it simple, what we can do is L is equal to 0 into zeros plus 1 into ones plus 2 into twos. Okay. So instead of putting a for loop, we can do this also. So what is the complexity of this algorithm? Yes.
We are checking each and every then O of n.
Yeah. We just iterating this entire elements once only, right?
Yeah.
Okay. So it's order of 1. Understood? Okay. Fine. Any doubts so far? That's it for today. The next class we'll start with the divide and conquer strategy. Along with that, we'll be seeing the searching and sorting algorithms.
Sir, I want to ask something.
Yeah.
How do we decide that further reduction in the complexity of an algorithm is not possible? We're trying to reduce the time complexity of an algorithm.
Yeah.
When do we decide that further reduction is not possible?
No, see, whatever like conclusion we come to, there might be further reduction in some or the other way. We'll try to see. Someone would have defined this as the stopping point, right? For prime numbers, someone would have decided this is the most optimal algorithm, but someone else has proposed this algorithm, which is a better algorithm. So like that, it keeps on evolving on time basis, right?
So
As
you
of
said
now,
that
like if it's a
we
if
never
it's a very
change.
if it's a simple algorithm, we can come to a conclusion. But if it's a very complex algorithm like a Darling salesman problem or a Hamiltonian
I
cycle,
have
those kinds of problems, we cannot come to conclusions also. Yeah.
an observation about the website. On the website, day 15 has been shown as day 16. I request you to correct that.
Okay. So it has been shuffled, huh? Is it shuffled? Okay, I'll just check and correct it.
Basically, day 15 is not shown. When you go to the website, day 15 is not shown there. Instead of day 15, it's day 16.
Okay,
So I
okay,
think it
okay.
should have.
I'll check it. I'll check it.
Check it.
Yeah, yeah. Okay. Fine. So shall we wind up?
Yes, sir.
Okay. So thank you all. We can meet in the next class.
Thank you.
Thank you, sir.